Hi, everyone. Welcome. This is my talk, to Patch Different on Star OS. It's really a talk about a journey of learning how to do Apple patch diffing, looking at vulnerabilities, and the reverse engineering of those vulnerabilities using patch diffing. And so it's my first time doing it in Apple, so we're going to learn together how this works. My name is John McIntosh, and the irony is not lost on me. And I work at ClearSec Labs. I want to start off by thanking InsomniHack for the conference. It's been a lot of fun. It's been well organized. We've been treated really well. So thank you, InsomniHack, for hosting me, for having me here. I'm excited to be here. I'll start off with the usual, like, who am I? You'll find me at social media at ClearBlueJar. By day, I'm a security researcher. In the evenings, I'm an open source dev and InfoSec blogger. And a little while ago, I wrote a tutorial called CVE North Stars. It was really the first time I taught myself patch diffing back in 2020. And basically, the idea behind that tutorial was to leverage CVEs as a way to dig into a new area of research. And that's what we're doing here today. We're going to start off here talking about binary diffing, try to get everyone on the same page. If you haven't done patch diffing or binary diffing before, I'll try to define it here for everyone. Really, the purpose when you do diffing is to find all those changes. How have the functions changed? How has the data changed? What does that give you insight into? It helps you focus and ignore everything that stayed the same. The why you would do it, like for reverse engineering, binary diffing is useful you can port your old work. Say you were 80% done reverse engineering a binary, a new version comes out, you're like, I don't want to do that work again. You can use patch diffing to kind of bring that work across, to match those functions up and save time that way. Vulnerability research is a primary use case as well, and that's what we're talking about today. How can we use patch diffing to go and see what the actual changes were for a binary, and how did they actually fix the issue, or did they fix the issue? Another use case is malware analysis. You can use diffing to compare two binaries to say, is this from the same malware lineage or things like that. Patch diffing, binary diffing is not a new thing. 20 years ago, the godfather of patch diffing, Halvar Flake, did a talk. And we're here 20 years later, still talking about the same thing. It's still relevant, still a useful reverse engineering technique. This is a screenshot from the tutorial that I wrote. And again, the idea behind this was to start with the CVE, a known vulnerability, do a diff, and then see what you can learn from it. See how that points you to vulnerable or buggy code. This tutorial was written on Windows, following several Windows print spooler CVEs, and looking in to see why they weren't fixing it properly and the root cause of those issues. I came out with some conclusions after I wrote the tutorial. I basically figured this, that patch diffing, I call it a single source of truth, or binary truth. You don't need a GitHub POC. You don't need someone's report to tell you what happened. You can go and see for yourself what happened between the two binaries. I said it provides clarity and root cause analysis. Again, you can see for yourself the changes that were made to see if it actually solves the security issue. It's not always so clear. There's a lot of reverse engineering involved. And that's the last part there is it's basically, with patch diffing, you can kind of take a CVE and create for yourself this small reverse engineering challenge and improve your competence as you go. So hopefully today we can improve, if you need it, your competence in how to do this for the Apple security ecosystem. Oops. Last year, I had the opportunity to release a tool called GDrift, which was a binary diffing tool that would allow you to do command line diffing of two binaries. I built this tool mostly out of convenience. I was doing a lot of patch diffing, using some of the GUI tools, and I was tired of clicking through. And so I made a tool that would allow you to take two binaries, run out on the command line, and output a markdown file with a summary of all the differences. And the summary there kind of tells you what has been added, what has been deleted, what has been modified. Quickly, I'll give you an overview of what has changed. Now I post some things online. I say, oh, look at the latest Windows kernel is out. Come take a look at all the differences. Click this link. And it's easy to go through and navigate that. So we're going to use this same tool today to look at Mac CVEs. And again, it's very easy for me to kind of post information now. Here's a link to this. I can deep link to a specific section. Go look at this function. It looks very either suspicious or this is where the root issue is. And it's kind of a useful tool for me. And what that did was make me really good at patch diffing on Windows. I got really good there. And then I also had some experience for Android when I would extract an APK, pull out the native binaries, and I could do some patch diffing there. I got pretty good in this space. But then I said, what about Apple? What can I do there? I'm not as familiar with Apple. How could I approach it? And this is kind of, again, what this talk will kind of hopefully teach all of us. It was my process of learning. There's some success, some failure, and we'll see how it goes. So what's different on StarOS? I keep saying StarOS, and this was new for me. In case you don't, like, StarOS is just a way to categorize all the Apple operating systems. They used to only have macOS and iOS. Now they have watchOS, tvOS, Vision OS, and they're all kind of merging towards the same kind of a hierarchy and architecture and all those things. But there are definitely some differences for each. And it was really coined by this book here, Star OS Internals by Jonathan Levin, which is an excellent book that I've not read entirely. I've read a few things. But that's where the name comes from, instead of saying macOS or iOS. But the basic process for diffing on Apple remains the same. You need to find a vulnerable version of your binary, a patched version, and then you use some type of SRE, or software reverse engineering tooling, to analyze it. You do your diff, and then profit. We'll see together what we can learn. If you go look for some previous research for Apple diffing, Safan Esser is a prominent Apple security researcher. He has a talk about doing diffing with using the tools IDA and Diaphora. And he digs into a iOS jailbreak here. There's another presentation, a story of Apple patch diff, that gives you some more information from 2019. And this talk's a little bit different. That talk was given by an excellent Apple researcher, and this one is just given by a researcher. That was done using IDA and Diaphora. We're going to use both Ghidra and Ghidriff to do the diffing, and a new tool, or not new to me, a tool called IPSW, and we're going to look at several CVEs, and that's kind of the whole point. IPSW is a tool without, I probably wouldn't be standing here talking to you today as confident as I am. But it's a iOS, macOS research Swiss Army knife. It's critical for our process today. We're going to use Ghidra to do the analysis of the binaries, and we'll use Ghidriff to do the diffing. And so that's like the high-level picture of the tools, and we're going to start. So we're going to use patch diffing as a kind of a gateway to a new area of research, a new area for me and maybe for you, or maybe not. And if I have any, you can tell me after where I'm wrong. But you can use patch diffing as a gateway, and we can focus on a single vulnerability or CVE to kind of keep us on a straight path as we go forward. We're going to lean a lot on kind of the giants, the security researchers that are prominent, some of their work, open source blogs, the documentation that's out there, and we're that little person on the rock leaning against that giant. I'm hoping to accomplish something in this space. So that was my intro, and here's the kind of the big picture. We're going to learn how to, what is the high level diffing strategy for StarOS. We're going to talk about Apple security updates. That's important for our process. We're going to diff something called IPSW. And we're going to look at how to diff the binaries, and then finally how to root cause them, and kind of dig into that. So for the high-level diffing, kind of the strategy we're going to use is we're going to look at 2 points in time. A new version of the operating system and the one before. And then we're going to take the entire operating system, look at all the changes that were there, ignore most of the changes, and try to focus on a single CVE. And with that, we can kind of create this scoped RE problem that's kind of a fun puzzle, if you're into that, or a way to dig into a specific type of vulnerability, if you want to go learn about that. So we'll start here. We're going to talk to this process the whole time, so I won't explain it, but that's what the full process. And, is it easy? We'll find out. So we'll start with Apple security releases. What are they? Basically, every month, Apple releases a report. This report contains several CVEs listed. It is all the CVEs that they fix for that release. You can see that they're listed by operating system, iOS or Mac OS, or maybe specific software that they fix security bugs in. If you click on one of those, you can see the specific CVE descriptions and the CVEs that were fixed tied to a specific release. In this case, there was something to do with accessibility. The descriptions are not always perfect. They're a little bit vague. probably on purpose, but we're going to kind of reveal some of these things with diffing. They've been doing this for a long time. These updates have been going out, I see here, since 2003, and they seem to release it on a Monday. I looked at the dates. Oh, it's always on a Monday. They always want to be different from Microsoft with their Patch Tuesday, if you're familiar with that. This is an older ad campaign for Mac. They're trying to keep themselves different and set apart. But they also have their Patch Tuesday or Patch Monday in this case. So again, in summary, it's a list of monthly security updates. There's other software on there. There is such thing as called a rapid security response. So if an ODA comes out or like there's something exploitation detected in the wild, they will release a quick update, and they won't wait till the end of the month. They'll just put a new update out there. A point I like to make for any kind of security update, whether that be a Patch Tuesday or the Apple security updates, is it's a double-edged sword, because you're fixing the bugs, but you're also kind of bringing a map in for maybe for the attackers or for the researchers looking to learn. But I say here, Apple doesn't disclose, discuss, or confirm security issues until an investigation has occurred and patches. So I'm going to use the word patches here. And what I'm saying here is that a patch, to me, is really kind of a public disclosure. If the software can be reverse engineered, then the patch to me is a public form of disclosure. We're going to use these updates in this big, long process here. So I think it's easier to see with this. We're going to start with the CVE. From a CVE, we're going to find the right Apple security update. From the update, we're going to tie that to the files that we need to go compare. We're going to extract those, analyze those, diff, and in the end, root cause the CVE. So let's keep going. With the Apple security updates, we've accomplished identifying a CVE of interest. You could just browse those, find one that you like, and see if you can figure it out. But we need to talk about IPSW. This term was new for me. I understood how kind of Windows updates were delivered and how they were secured. But for IPSW, this is basically Apple's software to deliver an entire OS in one file. It's actually just a zip archive with several Apple disk images inside and several other files. I don't even know understand everything that's in there. We don't need that for the thing that we're doing today. And you can find a nice summary of the IPSW, like the contents on the Apple Wiki, and that's listed there. But they're available from Apple directly. There's a third-party website if you want to go get one of these. It's ipsw.me. And you can basically just choose a device you want to go and get an IPSW file for, whether it be an iPad, iPhone, Vision OS. You'll click through and say, oh, I want to use this version of the iPhone. And that maps to a list of download links for the individual IPSW files. And again, those are the entire operating system in a single file. Really useful for us because we're trying to diff them. You follow through, you select your iPhone 15 Pro, you hit download, and it will give you a link from Apple CDN somewhere. The link contains the device, the version, and the build, which is helpful when you're trying to keep track of these things. And in my research, I read, sometimes these things are encrypted. I didn't know, this quote from the book Mac OS X Internals says, Apple has tried hard to discourage developers from getting their hands on those files, and therefore these files are encrypted. But that's from a while ago. That's from 2013. I went on a very trusted source, Reddit, and found out, someone asking the same question, someone answering, but this is from 8 years ago. Oh, yes, you can just change it to a zip, extract the file, and then you can decrypt them using the keys found on this wiki. And I see that there from iOS 9, and I went to the next version of the operating system, and they're no longer encrypted. So either Apple thought it was not worth it, or I don't know the real reason, but this means that now we can take a single IPSW file, we can change that IPSW extension to a zip, and then we can kind of go and see what's inside and kind of dissect that. And that's on purpose. If you mount some of the disk images, these are the names. It contains the base file system for the operating system. It contains something called the DYLD shared cache, which we'll learn about, and the kernel cache, which is a collection of kernel extensions and that kernel itself. But again, I'm new to Apple, and all of these files, they're confusing to me. And I don't really know how to approach them, so I need to go and find someone or something that can understand these. And so I found this tool, and it's called IPSW lowercase. It's a really amazing tool, especially without this, I wouldn't be standing here today walking through these CVEs with you. It's been around for about 5 years, and then, or I guess a little bit more actually, and it's getting more and more popular. Its tagline is, it says it downloads and parses the IPSWs and so much more, and that is true. It has a lot of features. We're not going to use all these features. I actually don't understand all the features, but we're going to use several of them together today. It actually has excellent documentation. You can go to the website, and there's several guides if you're looking to parse IPSW files or looking for more information about this. And you can install it with brew install on the Mac. You can run it as a Docker container, and it runs on Linux. It's written in Go, so it'll run, I guess, everywhere. But we need to know how to compare these, because we're trying to pull up these binaries eventually to get to a CVE. So we have a lot of questions. How can we download them? How can we compare them? How do we extract individual files from them? And as you could have guessed, it's IPSW to the rescue. Now, all these questions are answered actually with these commands. And so this is just here for reference, but this is how we're going to accomplish this together. So the main point there is, like, IPSW, the tool, lowercase, speaks uppercase IPSW, so we don't have to. And this is critical for me, and getting to the point where I can reverse engineer individual binaries. So if we want to go and download a specific build of an operating system, we found a CVE, we're like, let's go get that IPSW, the related one. We just go to the Apple Security Response page, we pick an OS version, and we pick the one before it, because you want to compare the differences between two. We select a device that looks good to us. IPSW provides you a device list. You can kind of walk through there and choose your favorite one. Then you download the right one and the one before. You can list all the URLs that are available to see for your device which versions of the OS are actually available. And then this is the process, right? Download the fixed patched IPSW, download the one before, and run this command called IPSW diff. It kind of handles all that complexity for you. Here's a quick command of how to do it. And you can compare the two firmwares, the two firmware files by running this command. And so this is, I approached this end of last year. Ran this command in IPSW diff. It's unpacking all of those files. It understands what's necessary to compare and how to dig into the IPSW. And then eventually I came out with this beautiful markdown result. And I'm going to see if I can click on this. I'll do the next one. The result on the left-hand side, there was my first time doing IPSW diff and getting a result. I said before, like, it is written in Markdown. I'm a big fan. My tool spits out Markdown as well, so you can copy-paste that in a README, copy-paste that in a GitHub gist, and kind of go from there. So I'm already liking this tool the first time I use it. And this is what it looks like late 2023. It could tell you about kernel extensions, entitlements, and it could tell you about dylibs and frameworks inside the dynamic or the DYLD shared cache, the DSC. And when I first tried it back in 2023, it actually didn't work as well for me because I was trying to do diff 2 IPSWs on the Mac operating system versus the iOS. And so I ran into some issues. It wasn't working quite like I expected, so I actually filed some issues on the GitHub, or on GitHub on the space. And within about 3 days, Blacktop, the developer, had responded with me, and I started to talk to her about what I was trying to accomplish. I want to diff binaries and make sure I can see all the changes, and so I can kind of reverse engineer that. And she responded right away and helped me in an enormous way on how to understand the operating system and kind of what the limitations of her tool could do, and also what it could do for me. So again, she responded about 3 days. I found out she's a security researcher at Trenchant. She's an expert Apple security and all things IPSW. I've asked her 1,000 questions, and she's like, "Oh, this is how this works. Oh, you should go look into this." And she introduced me even to a reverse engineering community that looks specifically at Apple software called Hack Different, and that kind of actually probably where this name came from for the talk. And so we now have these changes in here, and the diff now looks like this. And I was going to try to show you guys what this diff looks like and how it's useful. If I click here. Yeah, and so then the diff comes here, and you can kind of scroll through. You guys can see that or not. You click on one, you can say, what's been updated? What files have changed? and it can dig into the different files that have changed, and this will be the way that we can go and identify the file or the changes between each. So with IPSW and this IPSW diff, we now know what has changed between two versions of an operating system, and that's important for us to try to pinpoint the CVE within it. To look at binaries, you have to extract individual files from the IPSW. We can use IPSW extract to do that. If you want to do a file system file, this would be the command that you used. It works just fine. If you wanted to extract a private framework, I tried to use that same command initially. It didn't work, and I didn't know why. And I said, "Where is this file? I can't find it." I tried to find it on my local machine. It wasn't there. And this is because I'm naive, or I was new to the Apple ecosystem, and I realized the binaries aren't on the disk. Several of the binaries, like if they're libraries or private frameworks, they exist in something called the DYLD shared cache. It says, to save time on library loading, iOS's DYLD employs a shared pre-linked cache, and Apple has moved all the base libraries into it. So I won't find those binaries on the disk. And that was confusing to me. And then that was for iOS. And then for Mac OS, they incorporated that same cache back in, I think, 2020 with Mac OS 11. So here are the locations just for reference if you want to go see them on your machine. Again, coming from Windows, this is very confusing to me. You are loading libraries, you're importing these on the path, and they don't exist on the machine. But if we're doing CVE diffing, these are the possible locations we might go look. And what's good about it, in the IPSW, it kind of points to these directions for you anyway. It tells you what has been changed, what has been updated, and it'll direct you to extract the files in the right place. So we can extract files, we can determine the updates. How do we diff the binaries themselves? And that comes to the question of, if you're familiar with Apple Research, typically, I think IDA is probably the most popular. I think most reverse engineers, most screenshots I see from blog posts and everything else has IDA. And I think IDA is the prominent research there, but the question I had is, can Ghidra handle these Apple files? And I found so far, yes. And looking back at the changelog for Ghidra itself, there's about 88 references to Apple, something in the changelogs. So there's definitely new features being added or bugs being fixed. There was something added as it's a DYLD shared cache loader fix that was added last month in March. If you go all the way to the beginning of the change history for Ghidra back in 2019 when it was open sourced, there's changes there related to Mac. So it seems like it can handle it. The Apple Wiki actually gives us some information of what Ghidra can and can't do. And so I tried it myself back in February. And basically, I took this DYLD shared cache. It's a cache full of 6,000 binaries. And basically, I said, Ghidra, load that file. And it took overnight, but it did load all 6,700 files. And I was able to parse those and then analyze those pretty well. I just have some tips here, and this is more for you if you're going to look at these slides later. You want to set this parameter to true. This helps your type information propagate. For us, it doesn't matter. But the type information is important, and I can show you why. There's another project out there called IDA Objective-C types. You can use this for Ghidra as well, because Ghidra can take advantage of it. And what it does is it takes your decompilation on the left side with no type information and adds types to it. When you're trying to reverse engineer something, types are very important for your understanding. Again, in Ghidra, it looks very nice, and you have these types, and we'll see that with our examples. So let's try importing a file. We'll say Ghidra, import a context file. And then again, I was confused. It says container file detected, multiple files inside. And I think either I forgot or whichever, but Mac supports this idea of universal binaries where they pack in not just one architecture, but two. And that's so you can have the same file in a system, and depending on the architecture, the right one will run. And this, again, I just forgot. I'm like, okay, well, how do I get the actual binary so I can reverse engineer it? I did want to say this. They call these fat binaries because they include both architectures, and they have a tool to get those files back out, and it's called LiPo. So if you look at LiPo, you can use and cut the fat out, so you can cut the version of the architecture that you need to run and run that. The IPSW tool also supports LiPo, and then you can just extract the version that you need. So you can get the binary, you can get the right architecture, and then you need to diff the binary. Like, this is like the more like interesting part. And we're going to use Ghidra to do that, and more specifically, we're going to use Ghidriff, my tool, which just leverages Ghidra's analysis and does the diffing on top. And back in January, I made some changes to the tool so that it would support StarOS well. And this is a picture of Ghidra teaching my tool how to do this. I made the updates, and actually, we're going to see here in a minute if that worked well. It seems to have. And so the way you would diff with my tool is you would extract the binaries that you need. You have your vulnerable version and your patch version, and you run this command line. So we're going to see that now as we dig into the CVEs. So we're getting closer. We can extract files. We know how to get the right IPSWs and find the differences. Now we're going to try to root cause CVEs. And so one thing we have to consider when we're looking at CVEs and just think about is, while we're reverse engineering, is how are security issues actually fixed? Maybe there's some change in integer types. Maybe some additional checks have been added, or there's something to do with security. Even like a change around a mem copy, I get suspicious on, even though there's quite a few. These are just ideas for what to look for as we go through the diffing. Again, code changes, data changes, additional entitlements are all kind of useful in this process. And IPSW gives us that. So IPSW lowercase gives us the visibility of the differences between two operating system images, and Ghidriff tells us the code changes, and that's kind of the difference there. And we're going to look at these 5 CVEs. There's a use after free, timing side channel issue, time of check, time of use. You guys can read it. It's up there. We're going to get through here. And so for the first one, we're going to go through that full process. We're going to identify our CVE, get our IPSWs, and progress from there. So the CV of interest now is 2023-32-412. From the Apple Security Update, we can see it's something to do with telephony. A remote attacker may be able to cause unexpected app termination, like a denial of service, or arbitrary code execution. And then the use after free issue was fixed. And so the description itself kind of gives you some hints or some context of what to go look for. I mean, if you trust it. So we'll see how this works out. This was a security issue in both Mac and iOS, so that they were published in both. And we're going to look at the one from iOS. So we have to download our 2 versions of IPSW using our command here. Identify the 2 that we need. Go ahead and download those. And then we can determine the changes for the update. We run a command IPSW diff. And we see here from the table of contents, there were 98 kernel extension changes, or there were 478 binaries that were changed. And that's quite a lot of binaries to diff. So we have to find a way to navigate how to not diff all those. And so we have to learn how to map the binaries to a CVE. Now, there's no direct, how do you know which binaries to map to a CVE? We don't. This is part of the reverse engineering process. This is probably something you would get better at as you gain more experience. I will show you the techniques that I used, but people with more experience could probably do this a little bit faster. Again, we're going to leverage diffing here because we're not going to look at all the changes, or not all the files, just the ones that have changed. So that helps limit our scope. But if we start with just this description, telephony is the subject. Maybe that's a library. Maybe that's something else. And so we simply do this. We take our diff that we did of the IPSWs and we grep for the characters tele, and that narrows it down to, not 400 files. That's only 8 or 9 files. And then from there, we could extract those files. We could do the diff, and kind of figure out where those binaries are. So there's no single command to extract all the binaries that you need. So you still have to pull out each one either from the shared cache or the file system or another space. But this command here can help you kind of navigate where to pull them out from. You can kind of look at the results and just grep for the telephone related ones, and this will categorize, these are on the file system, or these are in the shared cache. And if they're in the shared cache, you have to extract the shared cache, and then you have to extract all the files, and then copy those files to some place where we can run the diff. Now, usually I name my files with the version information and the build information. And these are just here, so you can reference this later. And you can grab the source version of the file itself. And so to diff the binaries, finally, we're going to diff CV binary. We're going to use gdrift to do it. And this is what it looks like. I'm going to run gdrift on this library that I found with a specific architecture and version number. And finally, we're going to see the result. Now, this was one of the first ones that I ran, and I was actually pretty impressed with the results. If I can, again, click on here. This was the diff, and you can paste this on GitHub or whichever, just written in Markdown. You can kind of look at the summary. Looks like there was no functions deleted. Some were added. If you can click on it and go down, you can say, oh, this was the functionality that was added. We don't know why yet, but you can kind of go through the diff and look through that. Oops. And actually, when I saw the results, you guys saw that there were symbol names in there. It wasn't all unnamed function names. I realized quite a few things. I said, Ghidra can handle those symbols, and it does the analysis well. My diffing didn't find a lot of differences. It found very few. And that really helps with the reverse engineering process. All of a sudden, I was like, yeah, we can actually do this diffing, not knowing how it would fare against Apple devices, and I was excited about that. So let's root cause this CVE. I wrote attacker, use after free. Okay, there's some hints there, but another thing is a hint is that Google Project Zero submitted this bug, and if you know about Google Project Zero, they post their bugs and the reports on their site. So we're going to cheat a little bit, and we're going to use their root cause analysis here, but it's going to verify some things for us. Again, the report says there's use after free in this library, which is the one that we just diffed, and it's in this function, this decode function. This function results in leaving a dangling pointer and a merged header. I don't know what these things mean yet, right? And it's dereferenced, could be a double free or could be used after a free condition. I'm like, okay, sounds pretty serious. We can look in Ghidra and we can see what they're talking about. We can say, oh, there's a SIP message, add header. And in the report, it says immediately after merging the new header, SIP message add header deletes the new header. We can see that in the decompilation. Not knowing anything about Apple reverse engineering, Ghidra's handling this for us. We can go and see that. And then he actually suggests a fix for Apple. They says, thus the correct fix is to use SIP pointer vector header, merge header for merging. This function does not currently exist. Well, we just saw that it now does exist in the diff. And this was sort of a validation for me, like, oh yeah, this diff is working. And I can see the results, and they look pretty reasonable. And so for this one, we had the full details of the root cause from Project Zero. We proved that we had the right file, that Ghidra could handle those symbols, and that actually Apple followed the advice or Ivan's advice in this case. And so I was pretty excited about that. Let's go on to another one. And we're going to go a little bit faster now because I've taught you know now how to get all the files. So we'll start with this one. This one is core crypto. Something to do with RSA PKCS1. It's a timing side channel issue. Well, if we can download the correct IPSWs, we've already learned how to do that. We can do the diff. We can see the results. There are several files that have changed across the shared cache, and we'll do our trick of, okay, which ones are related to crypt? Well, in this case, there's quite a few. I think there was maybe 15 results. And looking at the results, it's quite a few to diff. So which files? Another trick you can use is to say, well, maybe there's some symbol files symbols within the binary that relate again to the CV description. You can use NM on Mac to go and see, and get some results there. Some again minimizing the number of binaries you have to diff. But then which ones actually have code changes? Because in the IPSW diff from the IPSW tool, it will tell you which sections of the code have actually changed. In this case, there was no changes to the text section or the text underscore text section, and so there was no code changes actually. And if I did the diff of that, that's revealed there too. There are no functional changes in the binary, and so that helps you to know maybe you can ignore some of those sometimes when you're trying to narrow down the binaries you need to diff. But for this example, libcrypto, there actually is text section changes. And so we can walk through that. We can do the diff. Oh, IPSW does support a filter, so you can actually only get diff results for binaries with code changes. So that is helpful. But we're going to look at libcrypto. And I'm not sure if you can see that from here. But once again, Ghidra handled the analysis well. The diffing is done well. There's quite a few changes. Like there's functions added, functions modified. They seem to be related to what the CV description is going to be. And we'll go back to that. But we're going to kind of shortcut this and look at the diff here. So in the decode function, for this PKCS1V that was mentioned in the CV description, on the left-hand side, we have a bunch of processing going on. There's loops in there. There's some mem copies. And the right-hand side, that's been replaced by a single function called CCRSA-EME, decode safe. And so in this case, we're looking at to say, they've replaced maybe some unsafe code with a safe function. And that's where the fix has taken place. So looking at diffing really quickly, we can narrow in on the area of vulnerable code. And now, they said it was to do with side channel attacks. Now, I'm not a cryptographer, but you can maybe speculate on this. Maybe that unsafe code had errors, returned that would reveal some or leak some bit of the key or something. I don't have the insight into that to answer that question, but we've learned some more from this CV as well, is that several files were changed. Some of them had no code changes, so we just focused on the ones that did. Ghidra can handle the symbols. And the decode function has been, now uses this safe API. And so these things are all kind of indicators of we're getting on the right track. Again, for this side channel issue, I was not able to root cause that, but it would put you in the right place to start. So look at another example. This one actually was more recent and actually had quite a bit of information, thanks to Mickey Jin, who's another prominent Apple researcher. He posted a blog post kind of detailing this CVE, and it was kind of a perfect example to use to prove that the diffing is working, and for my understanding and for my learning. It was a detailed blog. He provided an exploit POC, and there's even comments on how Apple fixed the patch. I'm like, this is perfect. So a real high level of how this works. It was a time of check, time of use. He would copy a file to a certain location, queue a service to go and take that file and do some processing with it. He passes a symlink to the legitimate service, so when the checks are done, time of check, they pass validation. But by the time it comes to copy over the file for a place where it's going to be executed from, he switches that out with a symlink. And that's kind of an overview of the vulnerability. And then he describes, and this is how Apple fixed it in 14.1. He says they added a check to copy file to check for symlinks. That's how I understood it anyway. And it says that the copy file will return -2, and now my LP no longer works. So I assume that was the case. Copy file callback function added a check and added a check for a symbolic link. And so now the exploit doesn't work anymore. I went and did the standard diffing process we did with IPSW diff. Yep, that file had changed. Yep, this file has two functions that were modified. They related to what Mickey was talking about in the blog. But my results for diffing didn't quite line up with what was shown in the blog, or what was implied. There wasn't a change for an additional symlink check. I found actually that check has always been there. So I thought maybe my diffing wasn't right. So I came back to bindiff, which is a really popular tool as well. It works with Ghidra, and I verified that bindiff, the diffing results also agreed with my results. So I'm like, I don't think I'm wrong there. And as I said, there was no additional check for a symlink file. So I had to dig into this a little bit more. And we could actually kind of go back in time with patch diffing. I went and pulled an older version, like even from 2020. And that same check was always been there. So that the check for the symlinks has always been there. So the actual root issue must be something else. And let's see. Oh, yeah. That's what I just said, is that they assumed that the copy file was changed. It wasn't from the diff. And this is what I saw. This is the patched version of the control flow. The little yellow section, which may be hard to see in the bottom left, is the success path. And what you see in this vulnerable version, or what I thought, is that you have a path, two paths to the success path. And in the patch version, you have a single path. And the difference between those two things are they're checking the results from the copy file to see whether it succeeded or whether it failed. If it failed, in this case, you have a second chance to come back on the success path. And I'm like, oh, I'm onto something. I'm getting somewhere. This is definitely it. I've got some good material for this conference. Here's the diff in a side-by-side view of the decompiled code. And essentially, the code on the left, the vulnerable code, just has a way, even if you fail the copy file, to get back on the success path. And the code on the right properly checks the result from copy file and does not go down the success path unless you or unless copy file was successful. But I still I wanted to prove this out. I wanted to know that this was the case. And I'm new to Apple research. Even understanding how this is decompiled, what are those functions? I wanted to understand that a little bit better because I was unfamiliar with what those functions look like on Apple. I was able to write a small test program using some of the same library calls. So this is, I'm not sure if you can see it. I guess you can. This is like a sample code of what, some of the functionality that was happening in the vulnerable function. It was a call to copy file, checking the results, and successful if it passed. And then I threw that into Ghidra. I said, oh, this looks like the code that I am reverse engineering right now. So it's a way for you to teach yourself, oh, this is how this should look and maybe what it looked like when it was original source. So my assumption was this, that the patch version did things properly. They checked the result of copy file, and if it didn't pass, it returned 1, and otherwise it would be successful. I assumed that the actual root issue is that or in this check for the copy file result, the error, they give you a second out. Or let me back up. When checking the copy file result in the vulnerable version, they check the error number once again. An error number is the result from a system call. And if it's 0, then it's going to go to success. I'm like, this must be what the issue is. I went and looked up error number. Again, system calls overload the meanings of error numbers. Sometimes it can be confusing. Note that a number of system calls, the error number is not always treated properly, I guess, for the results of system calls is what I'm trying to allude to. Here, I looked at the results for copy file. I found this entry here that says the entire copy is aborted at this stage. Any file system objects created will remain. Copy file will return -1, the failure case, but error number will be unmodified, which is that exit I'm talking about, that double check for that error. So I'm doing all this. I'm doing all this statically. I'm like, I'm getting somewhere. The file that you copy is this directory structure. And I looked at how copy file handled copying a directory versus copying a file. And copy file is open source, actually. So you can go and look, and I'm like, oh, this is it. This is the case. If the return value is copy file quit, meaning the symlink was detected, or that's one of the cases, set the ret value to -1, but set the error number to 0. And that little puzzle piece perfectly fits what I had assumed about how this thing was vulnerable in the first place. So I'm like, okay, let's go prove this out. This is where we kind of enter dynamic analysis, where we looked at everything statically before, and we're going to see what kind of plays out. So I took a McIntosh exploit, compiled that. I ran that on my vulnerable machine. So I have a virtual machine running the vulnerable version of the operating system. It does all the things it needs to do with the symlink tricks, writes a payload, and now it's waiting. And on the debugger, I set a breakpoint on copy file for the vulnerable service. And I looked at the stack trace and identified, yep, this is exactly where this vulnerable code lives. Let's see the result. And what I was expecting was that the result was going to be -1. And at the bottom here, you see a red read of x0, which is the result of the copy file function, and it's 0. So that's success. So I tried to dynamically see if everything I assumed statically was correct, but I could never hit the case that I thought was going to work. Actually, before this conference, I thought I was on the right track, and discovered on my way over that actually not the case. But what I'm saying is my assumption about the root cause, I'm not sure. It's close, and it fits the mold, but I've never experienced that case in dynamic analysis, and so my result is that static analysis was lying to me, or I've not yet, researched this and reverse engineered this enough. But I learned quite a bit, like in that process. We starting with like leaning on the experts. We started with a ton of information. It kind of zeroed us in on that scenario. We used diffing to kind of dig deeper, like what were the changes. And I wanted to say I leveraged dynamic analysis to confirm my suspicion and prove the root cause that I found, but I haven't done that yet. But I did learn quite a bit. So I was compiling code to make sure it looked like the code that I was seeing in the reverse engineering or for the decompilation side. And it was definitely, I think, worthwhile, but I still wanted to have some better bullets for you guys. But again, I can recreate the conditions, and maybe I just haven't tried hard enough yet. We'll see. All right, how we doing? Okay, we're getting down. This one's really fast. This is a sensitive information leak. It's from the TCC. There's another example of another CVE, and a logic issue was addressed. And I'm not sure what the TCC is, but apparently it's the transparent consent and control, protecting user data. That seems important. And what I'm trying to confess with this CVE is I have no way to map a binary to it. I looked at that BSW diff. There were hundreds and hundreds of changes that could possibly be it. But I did find this GitHub POC that told me the exact issue and the way that they fixed it. The too long don't read is they added an entitlement check to parsec D. Now, I don't know too much what an entitlement is. I know it's a way to lock down processes. It's a way to restrict access. And you can see those differences for the entitlements in the IPSW diff. But for me, this was not an example of success, but an example of, diffing doesn't always solve your problems. I had no easy way to map the CVE. I'm inexperienced in the Apple security ecosystem. I couldn't just leverage diffing to get the answer for this one. But I'm going to show you guys both the ways it works and the way it won't. Okay, real fast. Integer overflow. This was a processing an image. I did the diff. We look at the video decoder. So that's the only binary. Actually, the diff only had 16 changes, so not too many changes across this diff. This is the video decoder. There was code changes. It lines up with an image processing issue mentioned in the CV description. And this is like the ideal diff. You have one function change, and you know it was changed for a security issue, so you go and look at that single function change. Also, it said, does it say that? Oh, and again, that's project 0 here, just to kind of back me up, is that it was an integer overflow issue. And it tells you which function it is in, but what I want to say is, and it's open source. Apple is using this open source library within their operating system. And so even when this open source library was patched here, they had to update their binary. So just also good to know, and learn as you're approaching a new operating system is they're using open source code here. If you're researching this, maybe you go look for other CVEs that have happened in open source code and also are used by Apple. But just to prove this out, integer overflow, what Guidra saw was a change in one of the types for the integers. And I was just trying to prove out that, the diff saw this, and then you can actually go inside the open source code and verify this to say, they changed an integer to an unsigned code or unsigned integer there, fixing the integer overflow issue that they saw. This is a bunch of links for reference for later. And those are all the CVEs really fast. Yeah. I hope in all of this, maybe you learned how you yourself could go approach the reverse engineering CVEs on Apple. Kind of see the differences, maybe, or learn some things along the way where you didn't expect, and then know that you can leverage patch diffing or reverse engineering in general to kind of approach a new area of research and not know all the answers, but kind of lean against the experts and say, okay, let me look at this blog post. Let me try to recreate the work that they did and learn a lot from that experience along the way. And don't get overwhelmed by everything that you see. Kind of use patch diffing to kind of just focus just on what your problem is. It isn't magic. It's just another tool you can use in your reverse engineering tool belt. Success is not certain, and that's pretty good. So that's the summary. I'm out of time. I guess I'm keeping you guys just a little bit over. And that's it. Yeah, that's all. you have any questions?
Thanks for the great talk. So I'm wondering if you are debugging like binaries on macOS or any StarOS. Are you doing it just with pure LLDB, or are you using any plugins or maybe IDA debugger?
So that example there, and this is me approaching I just used LLDB for that one. And so I created a virtual machine. I used UTM and an IPSW file to create that really quickly. And then I'm using LLDB with none of the plugins. I know there's several plugins that will show me like the stack and right?
Yeah, I don't know any, but we are planning to support LLDB in Pwn debug, which you may be familiar from Linux.
Yeah, that'll be good.
Thanks.
Yeah.
Thanks for the great talk. I also wanted to ask another question. Do you have in mind to do the next step, which is like the exploit reconstruction? Because, we have the diffing, we know the root cause, but, as red teamer or pen tester, we like to craft the exploit. Do you think that can be also feasible? Or,
Yeah, so the diffing itself will kind of point you to this vulnerable area of code. And all of a sudden, you know that if I can reach this code somehow, and maybe you don't know the path, or maybe the path is very clear. Maybe it's an export that you can just call, or maybe you can backtrace, the function calls and say, oh, if I call this function, I can get to this space. And so that would be your starting point. And that's kind of how I treat it as well. For vulnerability research, I look at a CVE to understand a vulnerability. And if you try to develop an exploit, you'll just learn more and more as you go. Like what are the limitations? Are there timing issues? Is that what your question? Could I use this?
Well, it's just, did you plan to actually maybe go through those examples? Did you manage to do some exploit on those CV or those kind of stuff, as a demo?
So, I guess generally, I ran a different exploit, and what I did there, I was in the starting process. I guess I'm not developing exploits for all the CVEs, but that's how it would begin. If I want to go learn about more of like a time of use vulnerability, I would look at an example of one in a CVE. Then I would diff it and understand kind of the restraints and limitations or how to do it. And then also you can look for variants. Does this code exist somewhere else? And actually you can use diffing to do that. I don't have an example of that here today for SAR-OS, but that's definitely could do that.
Maybe for another presentation.
Yeah, that's right. Yes, right. Yeah. That's it. Thank you. Yeah, that's it. All right. Thanks, guys. Appreciate it.